So the first paper is an experience track paper from Google on network load balancing. Mubashir is a software engineer at Google, where he is part of the congestion control team.
Good morning, everyone. Today I'm going to talk about PLB, which stands for Protective Load Balancing. It is a host-based load balancing mechanism for data center networks. This work is a result of collaboration of multiple people at Google, and it is my absolute pleasure to present it on their behalf. Load balancing is a widely studied problem, and I'm sure you must be familiar with multiple works that have appeared in venues like SIGCOMM', ranging from centralized to host and edge-based solutions. Load imbalance poses performance and efficiency challenges in data center networks, which I will show in a bit. At Google, when we wanted to deploy the existing solutions, we were largely unable to deploy them. Many solutions require deployment of new switches or large changes to the transport or the edge. They were not designed with heterogeneity and incremental deployment in mind, which are necessary deployment features for Google-like production data centers to keep the cost and reliability risks in check. These concerns led to the design of PLB, which is a simple mechanism yet very effective. PLB leverages IPv6 support. It requires minor transport changes and works with our existing switches. It is used throughout Google, and post-deployment, it produced major gains. The switches as well as the applications. It is open source, and you're welcome to give it a try. So load balancing in data center network is actually a problem of minimizing the interference among the competing flows in the shared network. Data centers have path diversity, which means multiple paths exist between any two machines in the network. ECMP, the de facto standard for load balancing in DCNs, exploits this and aims to use the paths evenly by hashing the 4 tuple, which consists of source, destination, IP, and ports. This random hash is then used at the switch to choose one of the egress links. ECMP works well if the burst patterns and flow sizes are uniform, but data center workloads are Pareto distributed. That means that we are mixing a few elephant flows with the majority of mice flows. This uneven mixing creates uneven utilization along the links and lowers the effective bandwidth, which hurts the application performance. On the right is an example of how ECMP-induced imbalance looked like for busy TORs in a data center network at Google before PLB was deployed. We look at busy TORs because that is where load imbalance hurts the most. This graph shows the probability density function of load imbalance metric, Li, from 1 day's worth of data. Li is the maximum minus minimum utilization over TOR uplinks, where utilization is computed over a 30-second interval. Li, the metric, captures the spread in utilization, or rather link imbalance. Each Li sample comes from a single switch. On the left lower side is an example of Li calculation, where Li is 20 computed as 70 minus 50, as 70 is the maximum port utilization and 50 is the minimum. The TORs considered in this graph have on average about 70% utilization across the port for a significant portion of a day. Ideally, you want the Li to be as close to 0 as possible, which means that all ports are receiving equal amount of traffic. However, utilization difference, as you can see, between ports of a TOR can reach up to 40 units. So for example, if one switch port is at 100% utilization and another one is at 60%, then your Li is going to be 40. So intuition suggests that some flows on the congested links can move over to the ones that have spare bandwidth available, which is precisely the idea behind PLB. You sense congestion and repath. The key questions that you want to answer is where to measure the congestion and how to repath. We propose that transport layer is the best place to track congestion. Congestion control module already tracks the end-to-end congestion via ECN or delay. PLB can leverage that information to then make a repathing decision. For how to repath at the host, with a simple configuration change, switches can be made to use flow label field from IPv6 header in addition to the 4-tuple for hashing. The connection can then change the IPv6 flow label on outgoing packets to get a new random hash at the switch and probabilistically change the path. This simple change unlocks the ability for every sender to trigger a repath. Let's go through a simple illustration here. In this example, I'm showing that this orange dashed line shows one flow flowing from a source host to a destination host through the specified path. And as a step one, you sense congestion, and that triggers a flow label change, which probabilistically changes the path to a more congestion-free path. Now let's see some details and properties of PLB. PLB tracks the congestion signals which are already collected by congestion control module and mark a round trip as congested if the congestion is above a certain threshold. After several consecutive congested rounds, it waits for the connection to go idle. It does this to minimize packet ordering. This is because if the new path is faster, then the receiver may get out of order packets. If connection does not go idle, then after specified rounds have passed and the congestion still persists, then PLB does the force repath by changing the IPv6 flow label. PLB congestion state is reset, and we continue this process until there is no congestion. As PLB prefers to repath when idle, small flows benefit from this the most, as they have more tendency to have idle periods in between. PLB prefers to move flows, small flows first, and let the big flows be more sticky to their current paths. PLB and congestion control have timescale separation. That means that PLB waits for the congestion control to act and reduce the sending rate. But when congestion control cannot adjust the sending rate to reduce congestion over multiple rounds, it is then that PLB trigger a repath. And PLB models a thermal diffusion process where congestion drives the movement of the flows. The more severe the congestion, the more frequent the movement of the flows. PLB was deployed globally in Google for data center networks and backbone. It spans multiple continents and a massive fleet of machines, and the rollout was completed within just a few weeks. It was deployed for 2 transport stacks, TCP, which uses BBRv2 as congestion control and uses ECN as the congestion signal, and user space Pony Express, which uses Swift as congestion control and uses delay as the congestion signal. PLB gets the congestion notification from the congestion control module, so this makes the transport changes very simple. Only 50 lines of code were added for each transport. Google data centers already fully use IPv6, so no switch changes were needed there. But fundamentally, PLB only requires some minor sender code changes and a switch configuration change. Let's look at some results now. PLB produces gains across the ports, switches, as well as the applications. Let's look at some switch level data first. On the left is the same graph that I showed before with the dashed blue curve. This data comes from LI samples collected over a day from busy tours in a DCN. And just to remind you again, LI is the maximum minus minimum utilization over egress port, measuring the utilization spread. The solid orange curve here shows the new distribution for LI when PLB is turned on. As you can see, there's a massive shift in LI mass towards 0. Load became more evenly spread at switch ports after PLB. LI does not go to 0 as PLB reacts to congestion. If there is no congestion in a load imbalance state, PLB does not react. This LI reduction is translated into about 50% lower packet discards at tor switches for this data center. PLB also improves the efficiency of DCN core switches. I will show a different graph to illustrate this point. On the right, we show before-after distribution of maximum utilization among uplinks at all the aggregation switches in a DCN. Maximum utilization captures the headroom available at the busiest port switch port. Each sample comes from an individual switch like before, and PLB moves the traffic away from the most congested ports, resulting in a shift in a distribution towards the left, and the distribution becoming more flat around the tail. As maximum utilization at the switches goes down, that increases the headroom for transient burst, which can arise as mentioned in yesterday's Jupyter talk. This improvement also led to about 33% lower packet discard at aggregation switches. At such a large operation scale, top-of-the-rack switches across the fleet vary in utilization and the state of load imbalance that exists on them at a particular point in time. Here we show the effects of PLB for the full spectrum of switch utilization and the load imbalance in our fleet, and notice the regions where PLB is most active and effective. This is a 2D heat map colored by the percentage of change in normalized count of each bin. X and Y axis here are minimum utilization and LI metric respectively. The scales are normalized. These two quantities cover the utilization range of switchboards. It's easy to see that with an example here. For example, consider XY where minimum utilization is 50 and LI is 20. This bin contains the data points for which the switchboard utilizations are in 50 to 70% range. This graph shows the percentage change in normalized count for different such bins after PLB is deployed. Decrease is shown by a shade of blue, and increase is shown by a shade of red. The region where we want to be is shown in the green rectangle. We want to be close to 0 LI to have balanced traffic across the Tor uplinks, which is exactly what happens after PLB is deployed. Deep red shade around 0 LI suggests that more mass moved into this region after PLB was deployed. There's a corresponding decrease in mass from regions that have high LI that are shown by the blue shade. Though the effect is evident across the board, but it is more pronounced for the circled region, which contains data from switches with high utilization, an example of which I also showed before. This is where PLB is most active and helpful. Because of more severe congestion, PLB acts more aggressively to reduce imbalance. When utilization is low, PLB does not see much incentive to drive down the load balance, as you can see more white regions in lower utilization. The gains from the switch-level load imbalance translate into better performance for DCN applications too. The left graph here shows the effect on transfer latency for small RPCs of a storage workload. The transfer latency is the time spent between the first byte sent and the last byte act for an RPC. As PLB reacts to congestion, its effect is most evident at the tail, where it reduces the 99th percentile by 20% as it moves the small flows away from the congested hotspots. There is an interesting crossover in the graph, as you can see in the middle. PLB pushes more traffic towards lowly utilized link, which means that there is a slightly elevated transfer latency at lower percentiles. The right graph here shows the effect of PLB on application level. Here we are looking at deadline exceeded rate for a low latency file system. RPCs belonging to this application need to be completed within a deadline, and PLB reduced the median error rate by about 66% for this application. Now let's discuss some deployment experiences. We observed that load imbalance exists at all levels of data center hierarchy: Tor, core switches, and WAN gateways. Edges have it worst. Aggregation helps at core switches, but load imbalance still exists that create hotspots. Any load balancing solution needs to tackle the end-to-end path. Hosts have the view of the end-to-end congestion of the path. Empowering the host to make the decision has the potential to also decrease the control plane complexity. PLB leverages the DCN host and switch features. It is incrementally deployable and coexists incredibly well with legacy or non-PLB traffic. With partial deployment, when competing with legacy traffic on a shared bottleneck, PLB-enabled traffic can move away to more congestion-free paths, leaving more bandwidth room for legacy traffic. We observe that congestion is a powerful metric to align traffic to the true carrying capacity along the path. Traffic engineering, or WCMP, control loops are on order of seconds to minute scale, and there can be suboptimality due to demand misprediction or workload fluctuation. PLB, meanwhile, can redistribute the overload on the links in order of RTT. So PLB complements traffic engineering, but it does not replace it, because routes still need to be provisioned to match the capacity to the demand. However, in existence of PLB, there is a potential for traffic engineering algorithm to be more flexible and simpler, allowing PLB to correct any minor routing efficiencies and remove some complexity from traffic engineering's end. Finally, PLB is a simple but efficient scheme to achieve link-level load balancing in data centers. It is fully deployed through Google DCNs and produces significant gain. PLB is a simple algorithm, which is its power, and as it incorporates heterogeneity across switch ports, transports, and topologies very nicely. Simple solutions are always attractive for adoption and deployment in large systems. They are less costly, have low reliability risks, and are easier to manage. Monitoring and reasoning about them is also relatively easier. See section 5 of the paper for more interesting interactions of PLB with some other mechanisms. Some future work includes theoretical modeling of PLB and tighter integration with traffic engineering to reduce some complexity from their end. Finally, PLB is open source. You can follow this GitHub link for PLB implementation in TCP BBRv2. And I'm also listing an email for you to send any questions. Thank you for your time.
It's really nice to see combining load balancing and congestion control. I was curious about this observation you had about packet loss reduction. You spoke in terms of percentages. Can you give me a sense of how large that packet loss was at the store switches before and after?
I cannot speak in exact numbers, but the top of the rack switches, they have more packet loss when compared to the aggregation switches, where the traffic engineering is deployed, which is an order of magnitude higher. It can be, but I cannot speak with exact numbers. Yeah, but it is significant. That's all I can say. Yes. Yes.
Very nice and simple idea. One thing that I'm slightly confused about is about your claims that you're more likely to move mice. Given that mice are short, you shouldn't have an opportunity to even move them. Rather, they are probably taking advantage of the fact that you have less congestion on the path. Or could you comment on why you think you can move mice?
So the TCP connections are persistent. So they're sending small flows, but they have idle peers in between. So actually, the TCP connection changes the flow label to move the future mice flows over that connection.
I see. So you're using a slightly different definition of mice. Thank you.
Yeah.
Thank you for a great talk. You said that once you're moving the path, you're still using the congestion control parameters from the previous path.
Right.
What is the impact on other connections that might be using that connection? Because according to the chart, it seems like your connection now got a better performance, but what is the impact on the others? Maybe your initial numbers on the congestion control on that path were too large for the others to the other path. That's the first question. And the second one, you said that you're doing the change of the path according to the signaling from the switch, for example, like ECNs and other stuff, right? Why not use, instead of changing to source routing, for example, instead of relying on the switch itself, and therefore do the balancing of the source?
For the second question, do you mean do the load balancing at the switch?
Meaning, if you're already taking an approach that you want to change the path, why not, and you're using IPv6, why not use source routing and choose your path on the source? That's for the second question.
I think the second question we can take a bit offline, so there's a bit of uncertainty. But regarding the first question, there's always birth and death process happening in DCN. So multiple flow TCP connection or flows are entering or exiting the system. So you're going to have that sort of dynamism in different kind of traffic flowing on different paths and having different RTDs. So when you change the path, that is just another sort of dynamic thing that happen in the data center.
You start very high, so it might be harming other connections that are using that path, right?
So most of the time, PLB reacts on congestion. So it is going to move the traffic on more paths that have less congestion. So in that sense, it is not going to affect those flows very badly that are on the congestion-free path already. Right. Thank you.
Okay, thank you.